Welcome back, kiddos. Here are solutions to some questions on page 135. This is block sliding down inclined plane type questions, and there are people, not blocks, in these situations, but block sliding down inclined plane with friction. Okay, so question 38. A crate on an inclined plane. Oh, it is a crate. Okay, calculate the magnitude, meaning amount of the acceleration, and then after 4 seconds, how fast will the crate be going? So, this is what it looks like. In this situation, we do not have friction. We have an inclined plane that is at an angle of 30 degrees with respect to the horizontal, and the crate, we're told, is 562 newtons, meaning that is its weight. So, we need to find acceleration. This would be a free body diagram. We have weight. This should be straight down. So, there we go. That's kind of cheating, I know. So, weight is pulling straight down. The weight we break into perpendicular and parallel components, meaning perpendicular and parallel to the inclined plane, and the plane pushes up on the block. This is the normal force, F sub n. Do not call that the net force, please. Okay. So, because the block is not moving into or out of the plane, these forces have to be balanced. Therefore, the net force, the result of all the forces acting on the block, the force that it actually experiences, the force that we use in F equals ma, the force that contributes to its acceleration, is this, mg sine theta. So mg sine theta is net force equals ma. Plug in our values. Notice how I'm doing weight divided by 9.8 to get mass. Okay, weight and mass are not the same thing. And solving for a, 4.9 meters per second squared, or half the acceleration due to gravity. The second part of the question says after 4 seconds, how fast is it going? So we go way back to our kinematics formulas. Final velocity equals initial velocity plus acceleration times time. Plug in and get 19.6 meters per second. Question 39. If the skier in example 6 were on a 31-degree downhill slope, what would be the magnitude of the acceleration? So, we have a skier, we have a slope at 31 degrees. Skiing, that's going to be fun. And here's our skier, okay, our box skier. And within the question, we're told what the coefficient of friction is. Okay, so it is not a friction on the surface. This is what we do. A free body diagram would look like this. We have the skier. Weight pulls downward. Friction pulls back up the hill. And the normal force pulls or pushes. Okay, so we would label that normal force, weight downward, and force of friction. Okay, so that's a free body diagram. Just the skier and the forces acting on it. To solve, we would then break the weight down into perpendicular and parallel components. We would know that these cancel, okay, which is why I haven't included them in the calculating part. We know that the what do we know? Alright, we know that this is the angle theta, and perpendicular component is mg cos theta, and the parallel component is mg sine theta. So, we've definitely done some questions like this. If you're confused about that, look at the block sliding down inclined plane basics video lesson. I think I went through and explained that kind of in great detail. So we just kind of assume that you can do that at this point. Alright, these forces cancel. This is the force that pulls it down a hill. This is the force that slows it down. So the net force is the force down the hill minus the force up the hill, meaning the parallel component of weight minus friction, and plugging in gives us this. Net force is F in F equals MA. Again, these are different. Net force equals mass times acceleration. F sub n, don't be confused and think that is net force. That is normal force, meaning the force perpendicular to the surface. Not the same. No, no. Okay, and I only say that because it's a very common mistake. So, dividing, we got mass, we have net force, we got an acceleration of 3.8 meters per second squared down the hill. Alright, fast. Number 40. 40 says, Stacy, who has a mass of 45 kilograms, starts down a slide that is inclined at an angle of 45 degrees, steep, with the horizontal. If the coefficient of friction between Stacy's shorts and the slide is 0.25, what is her acceleration? So, here's poor Stacy, just a box, and I have already broken her weight down into perpendicular and parallel components. If that's confusing, go back and look at that original block sliding down incline video lesson, please. Okay. Normal force and perpendicular component of weight are equal. They cancel out. The net force acting on Stacy will be parallel component minus friction. Net force is parallel component minus friction. Plugging in all of these values, where again frictional force is mu times the normal force. This is where we're getting the mu mg cos theta, mu mg cos theta, mu mg, am I repeating myself? Cos theta. Yes, I am. And solving, net force equals ma. Acceleration, we divide the net force by the mass to get 5.2 meters per second squared. Okie dokie. Number 41, last but not least, here we are solving for coefficient of friction. So we have the skier on the 37-degree hill, and example 6 has been moving for 5 seconds, so they speed up and they speed up and they speed up, and then they hit a slushy part or something. Oh wait, the snow suddenly, the friction, yeah, so they hit a slushy part, the angle isn't changing, it's just a coefficient of friction, and so all of a sudden, after speeding up and speeding up, they're moving at a constant speed. Constant speed means the net force is 0. Okay, so if it's a constant speed, the acceleration is 0, that's a 0, in which case, because from F equals ma, if the acceleration is 0, the net force has to be 0. That's where we get this. Net force equals 0. So, what do I say? Ah, yeah. If the net force is 0, we know that the pull, the gravity's pull, let me describe this differently. The parallel component of her weight, oh great, is exactly balanced by the force of friction. And we plug in, okay, notice how mass times acceleration due to gravity cancels out. Solving for mu gives 0.75.